Hello everyone, welcome back to Introduction to Artificial Intelligence System course. Today we're going to learn the basics of regression. So this topic would be the first topic of actually the machine learning and artificial intelligence concept. So far we have learned basics of linear algebra and optimization, which is just kind of revisiting the concept of linear algebra. So I guess you guys are already familiar with linear algebra and optimization, and this topic would be the really very first topic of machine learning. So for the regression and for today's course, we're gonna learn the first class of regression, and today we're gonna learn the linear regression, and we treat linear regression as an optimization problem, and we will expand the concept of linear regression to polynomial regression. So as some of you are familiar with the concept of regression, regression is kind of a set of statistical process for estimating the relationship between the dependent variable, which is often called the outcome or response variable, and one or more free independent variable. So for given x, the objective of regression is finding the best fitted model to estimate the value of y. So for the regression, we may first start with very simple case of linear model. So let's say for a given x and theta, we have a simple linear model that is for in general, y is equal to a function of x and theta. And for this case, let's say you did some experiment or simulation, so you got some simulation or experimental data like this. So for given different values of x, you obtain some relation, whereas you also obtain the value of the y. So in this case, if you plot this data, you may obtain like this. And in most cases, a linear model, as the term represent, is used to predict the yi, which is equal to yi is theta 1, theta 0 plus theta 1 xi. Yeah, so in linear model, by finding the proper values of theta 0 and theta 1, we may find some proper model that can represent the relation between x and y. So if you plot the fitted model, then the regression model can be represented like the red one. So as you can see here, your experimental data can be well represented by these regression model. So by using the predicted these model, you can predict any values of y based on this. Like for example, for unseen data, like for at the point x is equal to 2.5, based on this model, you may predict the values for the y would be like 2.4 or something. So that's how the regression works, and we're gonna learn the basics of linear regression today. So if we rewrite this concept in more detail in mathematical way, let's say x is equal to input and y can be think of as an output, and the objective of this linear regression is finding the proper values of theta 0 and theta 1 that represent the relation between x and y for the best fitted model. And the remaining thing is constructing proper matrix or proper mathematical expression for the data sets. And let's assume that you have some m set of data. So you have m pairs of experimental data. Then the thing you need to do is construct proper X matrix that where each column, X and Y matrix, where each column represents the data for each experiment. So if your first experimental data has the form of like this, your X and Y matrix can be represented as the X1 and Y1. And of course, for the second law, is also represented as x2 and y2. So as like this, you can construct these column vector where each law represents its data set. So here, for the convention, we're gonna write the predicted output yi as like this. So for this, we're gonna use the hat. So y hat is the predicted output. And for the theta 0 and theta 1, these would be the model parameters that should be found for representing the best fitted model. So remaining problem is that how to find model parameters of theta 0 and theta 1. And to find model parameters, proper model parameters that represent a proper linear model for the given data set, from now on, we're going to treat a linear regression as optimization problems, which means, as we learned in the last lecture, we're going to treat these linear regression problems as optimization problems for finding proper theta 0 and theta 1 that minimize the error between the predicted values and the truth values. So finding theta 0 and theta 1 such that satisfy the following conditions. So from the previous example, let's say we have some data set, and our objective is finding proper theta 0 and theta 1 so that we can find the proper relation between x and y. So let's say this red line is just the equations of y is equal to theta 0 plus theta 1 theta 1 xi. So our objective is finding proper theta 0 and theta 1 so that minimize the predicted value at this point between the error between the predicted value and the truth value is to be minimized. So let's say if you find some line like this, then the error would become very large compared to this red line, right? So we can think that this one is not a good predicted model, and this would be the good model when considering the all points near here. So our objective is finding proper theta 1, theta 0, and theta 1 so that we can predict proper model instead of this. And for this optimization, for convenience, we define a function that maps inputs to feature vectors phi. So from last slides, we have learned that y is equal to theta 0 plus xi times theta 1. And this linear model can be re-represented like this. And from this multiplication, we can rewrite this equation into a matrix multiplication. And from that, by rewriting this low vector as a column transpose of a column vector, we can rewrite the linear model as phi transpose times theta. And here we're gonna call this phi vector, which is equal to 1 xi, as a feature vector. So from this form, in this form, by writing each dataset element in each row, we can construct y hat is equal to phi times theta. And as you can see here, from this matrix form, which is equal to ax equal to b form, here A matrix, which is phi matrix, has a very skinny form. And our objective is finding x, and we know how to solve this skinny case, right? To solve this skinny case, we can use a least square method. So in summary, this optimization problem, we can rewrite minimize ax minus b form, which is phi theta minus y. And so from the first class, in linear algebra class, we have learned that the least square, the solution for a least squares, this solution for least square is can be solved by this. So solution is just nothing but phi transpose phi inverse phi transpose y. So from this we can solve the theta. And based on that, let's solve this least square problem using linear algebra that we have learned in the first class. So yeah, for that, let's say we have a given data set, like for x and y, like this. So in this case, the least square can be written as like this, where A matrix is so A is just the phi matrix. The phi is when we recall the phi matrix, it's just pi transpose x1, pi transpose x2, blah blah, where pi xi is 1 xi. So by keeping this in mind, what we need to do is constructing a proper A matrix. So for that, we're going to use a numpy np.hstack function, which stacks array in sequence horizontally. So horizontally, let's stack this whole matrix horizontally. So by converting this as matrix function, you can compute exactly the theta value, which is equal to this value. So by plotting this result, we can see a proper regression mode from here. And another way to solve this problem is using gradient descent optimization. So as we learned in the last time, we know how to solve this optimization problem using gradient descent, right? So our objective function is nothing but the a theta minus y transpose a theta minus y. So by calculating this, we can compute the gradient. So gradient is same as 2 times a transpose a theta minus a transpose y. So by using gradient descent optimization, what we need to do is updating this theta value with proper learning rate of alpha and few iterations. So for that, we will start with the theta value with random value, and by converting this theta to a matrix, and let's set alpha as 0.001. And for iteration, we're gonna compute the gradient descent for 1,000 iteration, and the df is the same as, let's rewrite this equation like this. So theta is theta minus alpha times df. So after this 1,000 iteration, we will derive theta will be derived as the optimal value. So by printing out this value, we will also obtain the similar value. And when you plot this result, we can also see that our regression mode properly represents the relation between the x and y. And lastly, we're going to solve this problem using CVXPy optimization. In the last time, we have learned a CVXPy is a very powerful tool to calculate optimization problem. So for that, we will show how to solve this problem using CVXPy optimization. So for that, let's first define the CVX as the theta as a CVX variable with the size of 2 times 1. So theta has the form of theta 0 and theta 1. And so for that, and next we will set the objective function, which is equal to minimize the CVX norm, which can be represented a times theta 2 minus y. So in the last time we have learned that in the CVX, the representing this mark, this mark represent the vector multiplications. So we define the L2 norm as the objective function. And by defining the problem without constraint, let's solve this CVX. And the result clearly show that they optimized the theta value. And similarly, we don't need to stick to use only L2 norm. So instead of using L2 norm here, let's use L1 norm. So for that, our objective function will be changed like this. So as you can see here, we changed the L2 from L2 norm to L1 norm. And the code can be modified by changing this part. And similarly, the result also show that the very similar value compared to the case where we use L2 norm. And by plotting these results by using L1 and L2 norm, we can see that our prediction regression model represents the relation between x and y both well. So from that, we can conclude that L1 norm also provides a pretty decent linear approximation. And from that, you might be wondering, then what's the difference between L1 and L2 norm? Their fitted models could be different in the case of where outlier exists. So the outlier here is the thing, meaning things that's situated away or detached from the main body of the systems. So let's see the case. And let's go back to our previous examples. And in addition to our data set, let's see the case where we have two additional outliers. So here, these 2 points can be considered as outliers because they are detached from the main body of the main data sets. So by considering these outliers, let's see how the results change. So by using CVX5, by using L2 norm and L1 norm, we can see that the predicted regression model looks very different formation. So by seeing these results, what do you think? Which model predicts the data set well? I think L1 represents the main structure, main data set, well compared to the case when we use L2 norm. Then why do you think these results was different? By plotting them together, we can see the difference better. So here, the case where we use L1 norm shows represent better regression model for the main structures compared to the case where we use L2 norm. So here, the reason what makes them different, you need to understand what makes them different. So here, you can understand the reason by seeing the definition of L1 norm and L2 norm. So by definition, the L1 norm measures the difference between the real value and the predicted value. In the case of L2 norm, we should multiply this value and then should calculate and then we calculate the square root of the summation of these values. So that means for these outliers which has very large errors compared to these values, these main structures, the error for these components would be like for L1 norm, it would be like 2. But in the case of L2 norm, we need to calculate the square of the error, so its value would be really high compared to these main structures. So in the case of L2 norm, we are giving kind of a weight values for these outliers. So because of them, you can see the predicted regression model has some slope for these outliers. So it's there is a kind of deviation for the main structures. Yeah, so far we have looked at very basics of linear regression, and from now on, I want to introduce very useful library, which is called a scikit-learn, for calculating linear regression. Scikit-learn is kind of a machine learning library written in Python. This is very simple and efficient tools for data mining and data analysis. It is accessible to everybody, so anyone can use it and anyone can reuse in various contexts. It is built to a NumPy, SciPy, and Matplotlib library. This is a schematic illustration for machine learning provided by scikit-learn. As you can see here, depending on the number of data and depending on the problem setting, there are many machine learning algorithms that we can use, and such as like SGD, PCA, linear regression, and something like that. And as you can see here, scikit-learn provides the platform to use these algorithms for your machine learning code. So by using scikit-learn, we can make our programming more easily and more proficiently. Yeah, so by keeping this in mind, let's make our regression model, linear regression code using scikit-learn. So for that, we first need to import the scikit-learn by using this command. So for that, similar to import like NumPy or something else, we need to write this comment like from scikit-learn. This one is the library, the name of library. From scikit-learn, let's import linear model. And for that, from that, let's define the variable for regression reg. And from that, from linear model, let's import a linear regression model. And by using the command, by using the function of lig jump fit, that's all for regression. So by setting reg as a variable for linear regression and fitting the fitting model using x and y, the results can be saved. Results are saved in this variable. So let's plot this result from calculated from scikit-learn. So these are the basic code for just plotting the basic our original data. And let's plot a straight line or fitted line that are saved in this rig variable. So for that, we need to first recall new data for XP, and the result can be predicted using rig.predict value. So this would be the y hat, which are the predicted value of y. And by plotting this as a red line, you can see that regression model represented in the red line represent the relation between x and y very well. So far we have looked a very simple case where only a single independent variable exists. So let's say y is just equal to a function of x. So that was the simple case that we have looked so far. And from now on, we're going to expand this idea to multivariate linear regression. As you can see, the terminology from the multivariate regression, multivariate. So here we will consider the case where more than one independent variable exists. So here the case will be written as like this. Y is a function of x1 and x2 and xn. So this in this case we call this as a multivariate linear regression. So let's consider a linear regression for multivariate data. And for that, let's consider the simple case. We have two variates of x1 and x2. So from geometrical view, we can consider as like this. So still, when we consider the linear model, it would be the form of the plane instead of a line, right? So we have two independent variables of x1 and x2, and we have one variable, dependent variables of y. So in this case, let's rewrite this equation in the form of matrix form. So for that, the only difference between the previous case is that we have a column vector of 3 by 1 case. And by stacking these in horizontally, we can also construct the y hat is equal to phi times theta, and here phi is just nothing but the size of m by 3 size. So as you can see here, this matrix form is just exactly the same in matrix representation from the previous case. So from that, the things to calculate the remaining things to calculate theta is exactly the same as previous case. Theta is nothing but the phi times phi transpose times phi inverse phi transpose times y. So let's see the multivariate linear regression using the example. And so for that, I made arbitrary data sets for x1 and x2 and y with some noise. So here is the scattered plot. So let's assume that we have this data set, and let's make a proper linear regression model that represents the relation between x1 and x2 and y. So let's make a linear regression model using multivariate data that we made from the previous slide. So for that, we first need to construct the phi and y matrix. So for that, A, which is basically the same as phi matrix. So let's horizontally stack these one column vectors and x1 and x2 data set. And then let's treat this A array as a matrix, and let's solve this linear least square problem using this equation. And by plotting these results, the result from theta, that one saved in this, we can see the regression plane represents our data set very well. As a final topic of today's lecture, we're going to expand this idea to nonlinear regression. So I guess you guys are already aware of the terminology of nonlinear, right? So compared to a simple linear equation, a nonlinear includes like quadratic or x is x square, log or sine or cosine. So except the linear equation, we call it as a nonlinear regression. And in the case of nonlinear regression, we can solve this problem actually is just exactly the same as linear regression. So here, the subtitle of this topic is actually we're gonna call this as actually linear regression. So I will explain in detail from now on. So the objective of nonlinear regression is finding doing some linear regression process for nonlinear data. So let's say for in this case, we can see some data points, and we can clearly see some nonlinearity. So nonlinearity. So here, although the data has the form of nonlinearity, we can solve this problem using linear equation. So the way to solve this problem is just exactly the same as linear regression, but the only difference is we'll use nonlinear features. So there are two methods for solving these nonlinear data. And the first one is constructing explicit feature vector, and second one is implicit feature vector, but using corner trick. But we're not gonna learn the second topic. So the only thing we're gonna learn for this lecture is constructing explicit feature vector. So let's say for polynomial features and radial basis features. Let's take an example of nonlinear regression. So for this, we're going to consider a very simple case of polynomial regression. So polynomial, as the word represents it, polynomial equation is the 다항식. So unlike the simple linear equation that only includes theta 0 plus theta 1 and x1. The polynomial equations has more term like x squared and blah blah and x nth term. So here let's take an example for a quadratic equation as an example. So for that, the highest term is a second order. So we have three variables to be optimized, like theta 0, theta 1, and theta 2. And for this quadratic equation, we can take the feature vector phi as the like this. So the first one, and so the first law would be 1, and the second law would be xi, and the third law would be xi squared. So by using these feature vector, you can also construct the phi matrix, which has the form of this. So from this, we can also construct y is equal to phi times theta vector. So as you can see here, the final term for this, the final form is exactly the same as the linear regression. So although the feature vector includes nonlinear term for xi squared, as you can see here from the y matrix, this equation is nothing but the linear equation, right? So that's why we call this we treat this as a linear regression. So although the terminology includes nonlinearity, our objective is solving a proper theta, not the phi vector. So right. So in terms of theta, we can treat this as a linear equation. So that's how we treat these nonlinear equation as a linear equation. So from that, of course, we know how to solve this equation. So by using least square solution, we can very easily solve theta for the optimized linear regression. So by keeping this in mind, let's solve this polynomial regression using Python. So for this, let's also first generate some data sets that are represented for that will be used for an example. So for that, I randomly generated this example for x and y. And for the data set, to find the proper polynomial regression model, the way is exactly the same as the previous linear regression cases. So for that, we first need to construct a matrix which is equal to the phi matrix, which is just horizontally stacking the 1 and x1 and x1 squared term. So this can be realized by using the comment for np.hstack. So the first column and the second column and the third column. And by treating this NumPy array as a matrix, and by solving this equation using the least square form, we can find the final theta value. So theta will has the form of this theta 0, theta 1, and theta 2, which is just exactly the same for which should be represent the following quadratic equation. So by plotting this quadratic equation, we can see that the polynomial regression properly represents the relation between x and y. So let me summarize today's lecture. So today we have learned the basics of linear regression. So although linear regression may seem very simple, so it may seem some limited, but it is very powerful because its input features can themselves include non-linear features of data. So as an example, we have shown how to calculate polynomial regression. So we have shown how to solve this polynomial regression by treating this as a linear regression. So polynomial regression is kind of a linear regression on nonlinear features of data. So what does it mean is that by treating the phi vector as a nonlinear feature vector, we can solve this polynomial regression as a linear regression. So for that, the only thing you need to do, you need to calculate is least square loss, which is nothing but the pi transpose pi inverse pi transpose times y. So this one can be solved using numerous optimization methods that we have learned in the last time. Yeah, so that's it for today's lecture, and thank you for your listening.